speak about aspects of duality and two categories.
Sorry about that, and thanks very much for the opportunity to talk. Okay, so my talk is going to be also on this general scheme of trying to understand space-time and quantum theory and everything about that. But a slightly different approach, but also has been present in the previous talks, is due to a range of authors, and I first learned it from the papers of Byers and Dolan, but I've seen it, then I subsequently saw that it also was in the papers of Kuki and Abramsky and other authors. Basically the idea is that you want to, rather than study a space-time or quantum theory directly, you make sure you understand the language in which it's expressed in first. And hopefully once you understand that language, and apparently it's not the language that we're familiar with, the language of sets and functions, but it's sort of a different language, and it's the language of categories with duals, and possibly higher categories with duals. The contention is that once you can express it that way, then you might be able to understand these things more easily. Okay, so here's a quote from David Caulfield. And category theory allows you to work on structures without the need first to pulverize them into set theoretic dust. That's a nice turn of phrase. And to give an example from the field of architecture, when studying the Notre Dame Cathedral in Paris, you try to understand how it relates to other cathedrals, and then to earlier and later cathedrals and other kinds of ecclesiastical building. What you don't do is begin by imagining it reduced to a pile of mineral fragments. So that's sort of, you don't try and imagine it as a set. You first try and work out the relationship with other structures. So let me continue with some quotes. So St. Augustine had a similar idea. He said, when in Rome, do as the Romans do. If you want to understand space-time, you must feel like a space-time, you must become a space-time. Okay. So I come from South Africa, and there's this proverb in South Africa called, it goes, Ubuntu, Ubuntu, Ngabantu. And it's a Nguni proverb, and it's sort of a very wise thing, and a white man like me will never be able to understand it. But luckily there are textbooks which we can go and look up what these things mean, literally at least. And if you just look at those words, it's a person is a person, so Mtu is a person, and is an article, like a or the. And I've translated it there for you, but the main thing is that a person is a person through other people. You're not a person unless you have other people around you. I am a rock, I am an island, that kind of thing. And that's a beautiful expression of the sense of community in African communities. And related to those of you who've got Linux installed will recognize these words like Ubuntu, because Ubuntu means the art of, or the personness. It's the personhood. It's what you are, the essence of being a person. And that's what Ubuntu actually means. And there's another one even, which is on, if any of you have watched The Gods Must Be Crazy with those Bushmen, they also have an even more profound saying, which no one can understand, but it goes, clear. And basically, they think it means diverse people unite, but only they can understand it, but it's a similar thing. And finally, Forrest Gump had a similar thing. Because it said, well, I won't, she had something there. It's what you do is more important than what you are. So the basic thing that gave us an idea that space-time and quantum theory are related is that if you roughly think of quantum theory as being represented by Hill, so quantum theory is sort of Hill, and space-time roughly, we talk about NCOB, when mathematicians talk about NCOB, they mean cobordism, so processes which take one space and become another space. And these are categories, and the objects of this category are n-1 dimensional spaces, okay, oriented, that's why there's a little arrow there. And the objects of these are finite dimensional Hilbert spaces, and the morphisms are things that go from one space into another space. So here's one space here at the top and one space at the bottom, and it's a morphism of space, so it's a space-time. And the other ones are linear maps, and things are starting to look, well, things looks like we've got the same things on left and right side, and continue. Here we've got a monoidal thing, means we can take two things and get a new thing, just take disjoint union. And if you've got two Hilbert spaces, you can take the tensor product. And tensor product is slightly profound. It's not the direct sum, it's the tensor product. We'll see more about that later, but here's the crucial thing. This is where it differs from set, is that you've got a way to reverse a space. You can take the opposite orientation. This is sort of CPT duality in physics. And in Hilbert, you can take the conjugate Hilbert space, with scalar multiplication acts conjugately. You can't do that with sets. And the same thing, you have duals for morphisms. You can turn a space-time upside down. Time reversion. Okay? And that's called M bar. And the same thing, here's this profound thing about Hilbert spaces, you have an adjoint map. And you can't have an adjoint, there is no adjoint map in sets. And so here's the thing which first made me believe that, wow, this is really cool, because this is the first time I could really understand what quantum entanglement was all about. Because in the picture, quantum entanglement says that the combined system is more than the sum of its parts. And just in one little picture there, it sort of summarizes it schematically what's going on. And you can only draw these pictures with literally with space and time. You can't understand it with functions. So these are the rough ideas which led people to believe in this principle that we should really look at this language more closely. Maybe it will explain to us more about space-time and quantum theory. So Bayes and Dolan have this program, and they started this big series of papers, and the first paper was HDA 0, high dimensional algebra 0, and they were saying that a unitary n-dimensional TQFT, which means a topological quantum field theory, basically is just a simplified mathematical notion of what a quantum field theory is about, is a unitary representation of that cobordism category, so that thing on the left-hand side, on the thing on the right-hand side. And that makes sense because they're both the same kind of thing, so it makes sense to represent one on the other. Okay? But now I've sort of upped the ante and I've actually gone into n categories where previously those were just categories, but it's the same kind of idea. N categories, you've got objects and morphisms. Now you've got morphisms going between the morphisms and so on. But you don't have to worry what that means exactly, but all you have to know is what it means graphically, because that's the only thing that matters. If you can't express it graphically, then it's not simple enough to be a profound principle. Okay. Cobordism hypothesis. This is a really cool thing. So in that paper, they made this hypothesis, a remarkable hypothesis. It's saying that this n category of cobordisms, that thing that we had on the left-hand side, with just the little pictures of spaces and space-time, but now we've got to add ways to go from one space-time to another space-time and so on. But it's the free weak n category with duals. So by duals, meaning you can reverse the objects, you can reverse the morphisms in the way I was demonstrating. And saying that it's free is really, this is a remarkable link between topology, because this has basically got an incredible amount of topological and geometric information all summarized in there. And it's saying it's the free weak n category with duals. So if you can understand what an n category with duals is, you've immediately got a grip on a sizable part of space-time geometry and also on quantum theory. And that's the introduction to my talk. I just wanted to say that's where I'm coming from, is sort of, if we can understand duality, then we can understand space-time and quantum theory better, hopefully. So I'll skip the extra stuff. And so there's this nice diagram for working. So I'm going to walk now just with one small little aspect of this thing. I'm going to be talking about duality in two categories. And so there's this nice diagrammatic notation for working with two categories. If you don't know what two categories is, you just got objects, little dots, you've got morphisms, little process things, and you've got two morphisms which go between the morphisms. That's all you need to know. And the traditional notations, this globular notation, okay, traditionally they don't color them in, but I've colored them in for you, and there's a sort of even nicer way to write down some of these things. It works, it helps you to make calculations, and basically you take the Poincaré duals. So normally you would say, here's an object, and here's a morphism, here's another morphism, and here's a two morphism going between the morphisms. And now you draw it in string diagram notation. So this is the traditional notation, this is the string diagram notation. That object, which was a dot, becomes a planar region here. And that one becomes another planar region. And a line here becomes a line, but you represent it sort of like as a little line like that. And this thing here, which was sort of a planar region over here, now becomes a dot. So that little theta is sort of a dot. You just take the Poincaré duals, and working in this Poincaré dual picture, a lot of the identities and equations turn out to be a lot easier to manipulate. And so we used to write composition just by juxtaposition like that, and now we write it like that. So that's composition of one morphism. in a 2 category you can compose the 2 morphisms as well. You can compose them horizontally like this, and now that it looks like that. So you just arrange the blue and the purple and so on. It's exactly how you would think you would do it if you just take the Poincare duals. And the vertical composition, sort of, you can compose 2 morphisms vertically as well, and this is what it translates to into string diagrams. So,
how do I know that well, F goes from A to B, but G is parent to that? Sorry, they're all parent diagonals.
So F goes from A to B and G goes from B to C. You mean this one over here?
So I just read the string diagram from right to left.
So I'm a right to left person and a top to down person. So you have to make some choices with these things. So I'm one of those right to left, top down people. Okay. Or dying breed, I think. My supervisor prefers it the other way. Right, so that's just a notation for working with these things. So one thing I want to point out here is that if you sort of want to object to this point and you think this only works, if you're a high category fundi, you might think, well, this is only about strict things. There's such a thing called a strict high category and a weak high category. But what I want to say is that string diagrams are beautiful notation even for fully weak high categories. I'm not doing anything strict here. Basically, you just got to make sure that at any point at which you have a string diagram, the input, so this is a diagram for 2 morphism, and it has an input and it has an output 1 morphism, and you've got to have a parenthesis scheme understood in each context. Once you've understood that parenthesis scheme, which will always be the case in this talk, then that 2 morphism is there's a unique way to evaluate it, no matter in which way you insert associators, and that's a result called coherence for 2 categories. But so, just if there were any people who wanted to object at this point, it really is a rigorous notation. Okay, so now we're going to go on to these things. So what I'm going to be talking about is adjunctions in 2 categories. So those of you might know about adjunctions in categories. It just means category is a collection of things, and here's another collection of things. And so say this is England and this is France, and an adjunction between them means that if I go and visit my friend in France and I speak to him there, it should be the same as if he comes and visits me in England and I speak to him here. That's what it means to be an adjunction. And you can generalize this to any 2 category. Well, I mean, this is serious stuff. And I'm going to be talking about how you have to be a bit careful about how to do that, and this is what I'm going to be talking about. So we've got this 2 category, and we're going to be talking about ambidextrous adjunctions of a morphism. So you've got a morphism from A to B. Ambidextrous adjoint is a morphism which goes the other way, from B to A, from France to England, equipped with unit and co-unit 2 morphisms, which I'll explain just now, which express F star as a right adjoint of F, and also unit and co-unit 2 morphisms express F star as a left adjoint of F. So you've got things which say that it's a right adjoint and things which say it's a left adjoint. So you've got a lot of data here. You've got your thing going from B to A, so he has B and he has A, and you draw it with a little arrow going up. Traditionally, F star is drawn with the arrow going up, and F is drawn with the arrow going down. And these data here are unit and co-unit things, so this one goes from the identity to F star F. This is just something which happens when you express an adjunction abstractly. You have to express it through these co-unit and unit 2 morphisms. And so it goes from identity to F star F, and then the unit goes from F star to identity, and so on. But you got the point I want to stress that you've got the morphism going the other way, and then you've got a bunch of data that you have to pick. Okay. So together they form the objects of the ambijunction groupoid. Ambijunction means ambidextrous adjunction. So you get a groupoid, so the object of the groupoid is one of these guys. And a morphism from one of these guys, so from one adjoint of F to another adjoint of F, is a 2 morphism, going from this adjoint F star to another one, F star prime, such that this 2 morphism is compatible with these structure maps. So it means that if you do this little thing here, then you can pull the thingy over the thingy. So I'm not going to explain that diagram, but I just want you to, hopefully it's self-explanatory. The point is that the adjunctions, the choices of ambidextrous adjunctions for a given morphism form a groupoid. And it's called the ambijunction groupoid. Okay. So let's get some properties of this ambijunction groupoid. So we write like this for the set of isomorphism classes. So that's the isomorphism classes of adjoints. And now you have some properties of that, which will be a lot of higher category theorists or category theorists will recognize this. So if it's not empty, in other words, if there is at least one ambidextrous adjoint, then there's at most one arrow between any two objects in that groupoid. That's very important. There's no higher symmetry. And secondly, that once you quotient out by those things, you take isomorphism classes, then that set, in other words, a set of isomorphism classes of ambidextrous adjoints of F is a torsor for a certain group. It's the group of automorphisms of that morphism F. So let me just explain that. So if you've got an automorphism from F to F, then it acts on an ambidextrous adjunction by twisting the right unit and co-unit maps. So here's an automorphism of F, and I act on an isomorphism class. I keep in the same F star, I keep the same unit and co-unit, but I twist the right ones by adding a little alpha there. So here's a map from F to F. There's automorphism going on there, and there's alpha inverse. So what I hope you gain from this little lemma is that there's very good control over that ambijunction groupoid. The isomorphism class is a torsor for the certain group, the gauge group, if you like. Seriously, you should think of it as a gauge group. Okay. So now defining my main thing I want to define in this lecture is the even concept of an even-handed structure on a 2 category. So the first thing we have to check is now, suppose you've got a 2 morphism going from one morphism to another one, F to G, and that you've made choices of ambidextrous adjoints. You've chosen one for F and you've chosen one for G. Then you can take the daggers of these things, right? It's like taking the dual of theta. It's going to be a morphism from G star to F star. 2 morphisms, sorry. But there's 2 ways to do it, because you've got right adjoints and left adjoints. You can either use the right adjoint maps, which would be this one here. So yeah, I've only used the right things of G and the right thing of F, and that's why it's got a right dagger. And yeah, it's got a left dagger because I've used the left adjoint thing of G and the left adjoint thing of F. There's 2 different ways I can take the adjoints. And one quick thing you can prove with string diagrams is that whether these things are equal or not only depends on the isomorphism classes of the adjoints you chose, not on the specific ones you chose. Okay, so that's an important fact. And they're not equal in general. I mean, because they transform differently under the gauge group. But now we can go on to our definition. So first we say that a 2 category has ambidextrous adjoints. Every morphism has at least an unspecified ambidextrous adjoint. You don't want to specify them. So now our main definition is that an even-handed structure on a 2 category with ambidextrous adjoints is a choice. So we don't choose an actual adjoint, we rather choose an isomorphism class of adjoint for every morphism, such that the isomorphism class of adjoints of the identity is just a trivial one. If you do the G composed with F star, then it's F star composed with G star. And those are actual equality symbols. I'm doing fully weak high categories here, but those are equality symbols because I'm dealing with isomorphism classes. And finally, the most important property is that the right dagger equals the left dagger. So that's the constraint which relates the right unit maps to the left co-unit maps. Okay. So an even-handed structure on a 2 category is a way where you've got a sort of concrete hold on the relationship between the right adjoints and the left adjoints. So geometrically, you can think of this as a sort of a trivialization of the ambijunction germ. I just put that in because I like these impressive sounding words, but basically you think to every morphism you've got a sort of torsor here, because this is the collection of isomorphism class of adjoints, and Aut F1 is the gauge groups acting on that, and Aut F2 is the gauge group acting on that. And you want to take a section, you want to choose a specific one in there. And that's sort of similar. I'm just saying this because I want to demonstrate that this is not just abstract nonsense, this ties in with geometry. That it's similar to this. There's a notion of a spin structure on a manifold, and you can actually reformulate that as a trivialization of a certain germ. So it is sort of a geometric concept. So I've got a lot of things to say. So monoidal categories are 1 object, 2 categories. So now we've got our definition, an even-handed structure on the 2 category. let's go and test it out in some basic cases. So the most basic case of a 2 category is a 1 object 2 category, commonly known as a monoidal category, where you've got a, because a 1 object 2 category means that you've got one object and you've got morphisms, and you can compose the morphisms. If we re-index that and consider the morphisms as objects, then that means you've got a way of tensor producting 2 objects. So you've got a monoidal category. And now we can go and apply this definition to a monoidal category and compare to related definitions. But I think I'm going to skip this, and if there are any questions, if anyone sees anything interesting later, fusion categories, pivotal structures, so on, but let me just go on to the next one. So I'm just time up. Okay. Now we're going on to just good old, we're trying to do an even-handed structures on, so I told you abstractly what an even-handed structure on an abstract 2 category was. Now we're going to try and deal with the situation when those 2 categories was a subcategory of the 2 category of categories. That just means that the objects of our 2 categories are actual categories, and the morphisms are actual functors between categories, and the 2 morphisms are natural transformations. So everything's very nice and concrete here, no more abstract nonsense. And so let's see what it boils down to in this situation. So first of all, once you've got the situation, it's very convenient to take a change of variables. Don't deal with those units and co-units anymore. Rather express the adjunction with these adjunction isomorphisms. You see, this is that thing what I was telling you about visiting my friend in France. It turns out that an adjunction between 2 categories, you've got a functor from A to B, means that F is me making the trip from England to France, and that's me and that's my friend. If I go to France and meet my friend, it's the same as if I stay in England and he comes back and meets me. And so that's the left adjunction, but then there's also another one where he comes to France and speaks. You know what I mean? You can see the symmetry in the situation. So that's how we express left and right adjunctions in this concrete setting. And now, what about those left and right daggers? How do they translate into this picture? So suppose you've got a 2 morphism, a natural transformation. How can we express those right daggers and left daggers, which now go from this adjoint to that adjoint? And this is kind of quite a bizarre thing, but I'm sort of quite fond of it. But basically, what you have to do is we want to identify a certain morphism in a category. To identify a morphism in a category, there's this thing called the Yoneida lemma, which says you don't have to know exactly what that morphism is. All you have to know is how it post-composes and pre-composes with other morphisms. So it's exactly the statement of what you do is what you are. And so I don't know exactly what that theta dagger y is, but I do know what happens if you post-compose it. I do f followed by theta dagger y. It's exactly the same as doing this. Namely, so suppose I've got I take phi g inverse, I pre-compose with theta, and then I apply phi f. I'm probably going to need 5 more minutes just to explain that slide alone, so I'm not going to take that up. But what I want you to understand is that there's a way to identify what those theta daggers are in the setting of categories. And slightly subtle, but it's completely acceptable. Okay. Because there's a thing that tells you if you know what that thing is, then you know what that thing is. Okay, so now what is the end result? It says that, right, in this setting, in the concrete setting of categories and functors, an even-handed structure means that you've got a way from translating from a right adjoint. So this is, F star is an ambidextrous adjoint of F, and this is the set of all ways in which it can be expressed as an adjoint, a right adjoint of F. This is the set of all ways in which it can be expressed as the left adjoint of F. We've got a map from that set to that set. So in other words, a way of translating a right adjoint into a left adjoint. And that map must must transform correctly under isomorphisms and respect composition and so on. But the most important thing is that it satisfies this even-handed equation. Namely that it ensures that the theta right dagger equals the theta left dagger. And this post-inverse just means the morphism such that post-composition with that morphism equals this, and so on. Okay, so that's what an even-handed structure looks like in this concrete setting. Okay, now how do we get even-handed structures? So yes, interesting thing. So suppose I've got a linear category. So I just mean the Hom sets are vector spaces, okay, over field K. And a trace on such a thing is a map from every endomorphism. So from these, from the endomorphisms of every object to our field K, satisfying that it's commutative. Trace of GF equals trace FG, whenever that's defined, and non-degenerate, namely that taking the trace sets up an isomorphism from the Hom set XY into the linear dual of the Hom set YX. Because if I've got a map from X to Y, I can post-compose with such a map and take the trace. I'm getting some nods from the audience, but that's what a trace on a linear category is.
What's S?
S is just a spurious symbol I needed to denote this isomorphism. So S is the map, F goes to trace F dash. Okay, so just a remark here, if you want to think graphically, which is great, a trace on a category is the same thing. It's actually secretly not a category at all. Secretly, it's actually that category, which we thought was a category, is actually a monoidal functor from the category of planar cobordisms to the category of vector spaces. Namely, it takes x, y. So this thing, I'm not going to explain what this thing is. Hopefully these diagrams will. So it takes this little thing here, if you want to think of it as a little open string with boundaries labeled by x and y, it takes it to the Hom set x, y. And a little open string x, y, z developing into xz goes into composition. And this is your trace map. And that's the inverse map coming from the trace, or you know what I mean. So there's a concrete sort of graphical way of understanding what a category with a trace is. The cool thing about categories with traces is that they allow us to turn right adjoints into left adjoints. Namely, suppose I've got a right adjoint, so I've got one of these phis. Now I want to get a left adjoint, so I want to get a way to go from this Hom set to that Hom set. That's what a left adjoint does. If I'm in Paris and he comes to England and so on. Okay, so what I do is I start here, I do my little S map to go into the dual x, f star y dual. So there's like a symmetry in these Hom sets, you see. So I do my S map there, then I take the linear dual of my phi map, because phi went from here to here, so the dual is going to go from here to here. And then I take the S inverse now, going up again to get over here. You see? And so now, this composite now I'm going to write as phi capital T for phi transpose. And so it's this composite here. And that enabled me now to turn a right adjoint into a left adjoint. So that's the sort of category with a trace enables you to turn right adjoints into left adjoints. And then like a nice result is that if each of your categories in this concrete 2 category that we're working with, and I'm calling this the 2 category of linear categories. So if each of these categories comes equipped with a trace, then whenever we've got a right adjoint, if we send it to a left adjoint by this rule, by sending phi to phi transpose like this. So that's a way of turning right adjoints into left adjoints. And what I explained on the previous slide is that that's what an even-handed structure is. And indeed, it satisfies the axioms. So this stuff here is what makes sure that the even-handed structure is satisfied. Okay, so now I've got a concrete grip on, we're trying to understand what even-handed structures are, because we're trying to understand duality, and we're trying to understand duality because we're trying to understand quantum theory. So it's a long, long thing, but this is where we sort of come out to. And now we know what they are in the context of linear categories. So now let's look at concrete examples. So the first example, I'm going to give you 2 examples. The first example is the 2 category of 2 Hilbert spaces. So John Byers sort of came up with this thing in 1995, I think. And the 2 Hilbert spaces, to the Fundis, it's a categorification of a vector space. And to the ordinary people like me, it's just a very, very simple thing where you just got a bunch of simple objects and you can just add them. So, but in complicated language, it's an abelian category. So you've got, well, if you don't know what that is, don't worry. If you do, then you'll know what that is. As an abelian Hilbert-enriched category, it means that the Hom sets are finite dimensional Hilbert spaces. And the important thing is that it's equipped with antilinear maps, going from hom xy to hom yx. So you've got a way to reverse a morphism. You've got a morphism from x to y, you get a morphism from y to x. And that antilinear map must be compatible with composition, compatible with the linear products, and so on. And you can take these form a 2 category with linear functors as morphisms and natural transformations as 2 morphisms. Okay, so that's the 2 category of 2 Hilbert spaces. And a nice example to keep in mind is if you've got a group, a compact group, you take the category of unitary representation of the compact group. Okay, that's one of these guys because the hom sets are Hilbert spaces, and there is a way to reverse the morphism. You take the adjoint of the morphism. You have to have a compact group to do that because you have to average over the group inside. Okay, and basically that's all the examples of 2 Hilbert spaces. And the important thing is that every 2 Hilbert space comes equipped with a canonical trace. Now, if I got an endomorphism of object, I can take the inner product of that endomorphism with the identity. That gives me a number, and that's actually a trace. And so that means it's a candidate for one of these things. And in fact, so that means that the 2 Hilbert spaces, the 2 category of 2 Hilbert spaces has an even-handed structure. How can we express it in elementary terms? Basically, by saying that phi transpose, which came from abstract things in the previous category, can be expressed in sort of geometric terms as taking the star, then the phi star, and then the star. You know what I mean? But this here is the adjoint in the ordinary sense of maps between Hilbert spaces. Okay, so what I wanted to say is I'm interested in any possible connections, however spurious, with geometry, and this is sort of similar to the formula for the adjoint of a differential operator. And indeed, another spurious connection is that in the semi-simple context, even-handed structures on some collection of semi-simple categories is the same thing as assigning a non-zero weight to each simple object. And I think I'm running out of time, so I'm just going to cut that short. Let me just say the final slide is that that was the warm-up game, but the cool thing is that you can do even more geometric thing for the 2 category of Calabi-Yau manifolds, and basically you have to go to the derived categories. So I think I'm losing interest. If I look over the audience, I'm going to be very careful here. But basically, what I want you to understand from this slide is that there is a sort of souped-up notion of a 2 Hilbert space, which is really cool. You've got a Calabi-Yau manifold, this geometric thing. You take what's called the derived category of coherent sheaves on that, basically vector bundles on that space, and that's an interesting category. It comes equipped with a trace. JP Sir, basically there's this cool geometric thing which gives you a trace on this category, and it's called the Sir duality. And so that means that this 2 category, I'm defining the 2 category there, but it comes with an even-handed structure. Okay. So the important point about this is that this is a non-trivial thing. This has got to do with sort of results about complex geometry and so on, but it fits the scheme, and you can actually get some geometric information out of it. So let me just summarize. So remember what we're doing. You might have forgotten what we're doing, but I'm investigating duality in the context of 2 categories, especially from the paradigm of topological quantum field theory. I told you what an even-handed structure was. It's economical. There's only 3 equations. No messing around. It's flexible because you're free to choose the adjoint you need to. You don't have to. If someone chose an adjoint for you, then often your hands would be tied behind your back because you wouldn't be able to choose the one you want to choose in any particular calculation. It doesn't require you to choose an adjoint, as I've just said, so it fits these examples, which wouldn't be, because in these examples, there's no canonical choice of an adjoint. So the whole point of my formalism, or this formalism, is that you don't have to choose an adjoint. You only have to choose a way of turning an adjoint into a left adjoint. And it goes hand in hand with the powerful string diagram calculus, which I haven't used any of that, of course. And also it has geometric overtones, so the concept has a geometric overtones, and even the modular space of even-handed structures on a given 2 category. That's what I've been calculating in this last 2 slides. also has geometric overtones. And I personally needed this for a certain calculation, and that's why I developed this thing. But it came out of topological quantum field theory. But yeah. Okay. That's it.
Questions?
Are there any examples of sort of famous categories where you can't find these even-handed duals? You can only find sort of non-even-handed ones, or in all the examples of interest, can you always find these? For all these interesting categories with duals, can you always find even-handed?
Well, I don't know, but in the one object case, so we just got monoidal categories, and you look at the simplest case, that's semi-simple and everything. Those are called fusion categories, and that's an outstanding conjecture. Or in another paradigm of duality called pivotal structures, there's a conjecture which says every fusion category has a pivotal structure. In my language, every pivotal category has an even-handed structure. And it's still outstanding. So it's not clear that it can always be done. It's sort of like a cohomological obstruction, but they need to identify the crux.
What about just over the complex numbers or something? Does that make
Even
it
over
easier?
the complex numbers, it's not clear. Yeah. I was going to say things about that, but I skipped those slides.
You still have 4 minutes, according to my timer, before you're...
That's the question time. Okay, well let me say 1 or 2 words about that. So, basically, what you can show is that if you've got a monoidal category, then the modular space of even-handed structures, the collection of even-handed structures, is a torsor for the group of monoidal natural transformations of the identity. Right? So that's kind of easy, but the point is that we've got this group, we've got the gauge group of the equations. We don't know what the equations are. So we don't know, it's a sort of an interesting problem, and it comes up in physics a lot, I think, that you know how the equations should transform, but you don't actually know what the equations are. And there are some candidate equations you can put down, but you're not even sure if that has the correct symmetry group. I'll explain to you afterwards.
So what is the actual connection between your even-handed structures and pivotal things that have been discussed
Basically,
before?
a pivotal thing is where you actually choose a specific dual, and then because you've chosen a specific dual, now you have to say then a pivotal structure is a monoidal natural transformation from an identity to the double dual. And my one is basically the same thing. It's just I'm saying don't choose a specific dual, choose an isomorphism class of dual. Then you can actually write down exact equations, and sort of things are a little bit cleaner. It leaves you more flexible to do what you in your calculations. The other one's just a little bit awkward.
I don't know whether it's for channel, but there is this notion of trace which only requires the multiplicative structure, like a Charles-Street variety. Well, here you are relying on K-linearity. K-linearity doesn't fit well graphically. It's a property. Well, the Charles-Street variety trace is purely diagrammatic.
Isn't that in a monoidal category though? Because I'm talking about a trace. I'm just on a category. The only thing is that it's got linear composites. It's not a monoidal category. I'm just talking about a trace on a category.
Is there any connections?
Yes. If it's got a monoidal structure, then that will give you a trace. But the thing that you're talking about, you have to put some extra axioms on that. Basically, those are. So I'm working at a more primeval level here. But yes, those two things are very intimately connected. Yeah. I'm sorry I didn't get to the monoidal categories, but just ran out of time.
Any more questions? So let's thank our speaker again. Before we enter the discussion, I just want to say those